Imagine looking up at the night sky on a quiet night, wondering if the stars above will shine forever. Are we marching toward an inevitable cosmic finale, or is the universe somehow immortal? Scientists say that one of the universe's most likely endings is called heat death, a slow fade into darkness and lifelessness. In fact, one dramatic description goes like this: eventually, all the stars will burn out. No life, no heat, no light, only the corpses of dead stars and galaxies expanding into endless darkness. It's a bleak picture, but it comes from fundamental physics. Let's explore what this heat death actually means, how it will unfold, and why even this ultimate fate doesn't steal meaning from our lives today. In simple terms, heat death is the state of maximum entropy, a final equilibrium where the universe has used up all its free energy. Remember the second law of thermodynamics? It says that in a closed system, entropy, a measure of disorder or unavailable energy, tends to increase. Britannica explains this beautifully. If the universe is treated as an isolated system, its entropy must keep rising to a maximum. At that point, the cosmos reaches a uniform temperature everywhere, and no further changes involving the conversion of heat into useful work would be possible. In other words, once heat death arrives, nothing more can happen. Every difference in energy is gone. In everyday life, entropy shows up when, for example, a hot cup of coffee cools down to room temperature. Heat flows outward, and eventually the coffee and the room reach the same temperature. After that, you can't extract any useful energy from them. On a cosmic scale, heat death means the whole universe is that cooled-down cup of coffee. All energy has spread out evenly. Dark energy is pushing everything apart faster and faster, so galaxies recede from each other endlessly. If our universe has too little matter and lots of dark energy, as current measurements suggest, it will expand forever. This runaway expansion means the big freeze scenario, the same as heat death, is likely. Here, a NASA graph sketches possible expansion paths of the universe. The red curve is an accelerating expansion dominated by dark energy. In that case, space-time itself stretches constantly, and over immense time, all structures get pulled apart. Eventually, very far in the future, this drive toward maximum entropy will freeze the universe into a uniform, dark, and cold state. The march toward heat death takes place on unimaginably long timescales, but there is a rough timeline. Stars fade away. First, even if the expansion continues peacefully, stars will slowly exhaust their nuclear fuel. NASA's WMAP team notes that if the universe keeps expanding, stars will all but disappear after 10 to the power of 14 years. That's about 100 trillion years from now. By then, the last sun-like stars will have burned out, leaving behind faint white dwarfs and neutron stars. No new stars will form because galaxies become sparse. The night sky will go dark as every star's light flickers out. Galaxies go dark and decay. As the eons pass, galaxies drift apart into isolation. Their stars have died, and even the star's remnants begin to slowly cool and disintegrate. Some protons might even decay after approximately 10 to the power of 50 years according to some theories, turning matter into lighter particles. The galaxies become ghostly shells of very dim objects and radiation. Any remaining pockets of energy become vanishingly small. Black holes evaporate. In a far later era, the black holes themselves, those mysterious cosmic remnants, begin to vanish via Hawking radiation. Stephen Hawking showed that black holes emit a tiny amount of thermal radiation and lose mass over time, over about 10 to the power of 100 years. Even the most massive black holes will fully evaporate. As they emit their last quanta, the universe will have no large structures left at all. Scientific summaries explain that after black holes are gone, there are no energy gradients left to sustain any processes, leaving a barren, lifeless cosmos. thermal equilibrium, true heat death. Finally, the universe will reach thermal equilibrium. All energy will be spread out into an ultra-dilute gas of photons and elementary particles. The temperature of this final cosmos will be exceedingly low, close to absolute zero. Katie Mack, a theoretical astrophysicist, describes this state vividly. It's the maximum entropy state of the universe. All energy is just in the form of waste heat, with that heat being so scant it's around 10 to the power of minus 40 Kelvin. In her words, there will be no structure, no order, just a couple of stray photons, and that's the maximum entropy state. In this scenario, even time itself loses its arrow. Without entropy increasing, moments become indistinguishable. Essentially, nothing happens anymore. Try to picture that final cosmos, an endless, empty void with an almost imperceptible glow. No twinkling stars, no galaxies, just a few lone photons drifting endlessly. It would be unimaginably cold. There would be no warmth of any kind, only a faint background radiation near absolute zero. As Mack puts it, you would have this eternal state of a cold, dark, empty universe. It's a haunting image, like the universe as a cosmic tomb. For any imaginable observer, if there even is one, everything would appear frozen in time. No forces or gradients could do any work, nothing changes. Space itself keeps expanding, but with virtually no matter or energy left, those expansions are just empty stretches. In practical terms, it's absolute stillness. Some early thinkers even likened heat death to the last judgment of science. Once it comes, the cosmic stage is lit only by the cold embers of used-up energy. What happens after heat death? Once the universe sits in maximum entropy, most mainstream science says there is simply nothing, an eternal static cold. However, physicists have speculated about some intriguing possibilities. One idea is quantum fluctuations. A fluctuation is a small, temporary change in something, like a tiny wiggle in a system that's usually stable. In physics, especially quantum physics, fluctuations are spontaneous and random changes in energy that can happen even in what seems like empty space. These tiny shifts might seem unimportant, but over incredibly long timescales, they can lead to surprising events. Perhaps very far in the future, rare quantum events could spontaneously produce a tiny bubble of low entropy, or even a new universe. In the podcast conversation of Sean Carroll and Katie Mack, they mention proposals where a fluctuation creates a new Big Bang or a baby universe branching off. Carroll notes it's all super speculative and almost impossible to test, but it's one way people imagine a turnaround. Another thought is the so-called Big Bounce. Some theories suggest gravity or dark energy could someday reverse, causing the cosmos to recollapse, a big crunch, and then bounce into a new expansion, essentially a new Big Bang. In that view, the universe goes through endless cycles of death and rebirth. This idea is mostly theoretical and lacks strong evidence, but it shows scientists aren't ruling out new beginnings entirely. Finally, there are ideas about vacuum decay or other exotic physics that could disrupt heat death. For instance, the quantum vacuum we think we live in might be only metastable. Something that is metastable is stable, but only for now. It's like a ball resting in a shallow dip on a hill. It's not rolling away, so it seems stable. But with just the right push, it could fall into a deeper valley, a more stable state. In physics, we sometimes think the universe might be in a metastable state. It looks stable today, but in theory, it could suddenly snap into a new kind of reality if the laws of physics change. A lower energy vacuum could, in principle, nucleate and expand at light speed, completely changing the laws of physics and ending our universe suddenly. If that happened, it wouldn't be after heat death so much as an abrupt end. In short, in the heat death scenario, there is currently no clear next chapter that involves our universe continuing to produce complexity. Any rebirth would likely form a wholly new cosmos with no information from our universe. As one scientist phrased it, such new beginnings might occur, but it won't be in any way connected to us. It'll carry no information from us. None of this should scare you into despair, because it all happens on timescales far beyond human imagination. Remember, stars disappearing at 10 to the power of 14 years, protons decaying at 10 to the power of 50 years. These are numbers so large they're effectively a real long time to our brains. Even the evaporation of black holes takes around 10 to the power of 100 years. To put it in perspective, our sun still has about 5 billion years of life before it even becomes a red giant, and our galaxy will evolve dramatically long before then. More importantly, we don't live in that far future. As a recent Scientific American essay puts it, in the long run, entropy will spell the end of everything in the universe. But we don't live in the long run. We live now. In fact, knowing how vast and long the cosmic timeline is can make our present feel even more precious. In the cosmic story, heat death might be the final page, but for now the story is still being written, and that for now is enough.